All right, probability distributions. We're in chapter 5, 5.2. Binomial. What is binomial? That's what tonight is. So last time was just generally probability distributions. Tonight's binomial in particular. Now, what is a binomial? No, what is a probability distribution from last time? I know you did it and all, but it's kind of weird being asked that question. Like, I know you could crank out the homework now, but what is a probability distribution? Sometimes how the big
chance something might happen or might not happen.
Yeah, some probability things, yeah. And what about the distribution part? So that explains the probability part. Happen or not happen, good. And what about the distribution? What does that mean, probability distribution? To distribute means like to hand something out, right? Or pass it out. So probabilities are handed out. I don't know if you caught it. That's what a probability. Remember we looked at I just remember the gambling ones at the end. What was the earlier ones? Whatever they were.
I just remember dice.
Yeah, me too. There was something else though too. The insurance and anyway, there was different things that have different chances of happening, right? I don't know why none of them are coming to my mind. But a probability distribution means like different results and different probabilities. So distributing of probabilities. Like, didn't we have like, I don't know, I'll just do one of the game ones. We had the chance that you were going to win some kind of game, whatever it was, lottery, rolling the dice, whatever, and then lose. And there was a probability for each of those, huh? Maybe there was a 0.10 probability winning and a 90% of losing or whatever. Anyway, we had different kind of things that happened and different chances for each of those. That's what a probability distribution means. A distributing, a passing out of different probabilities. Right? Was any of that news to you about the gambling stuff? It made me think of it. I was out of town both Saturday and Sunday. Soccer on Saturday and visited my daughter at Cal Poly on Sunday. Anyway, and so we drove by and I see all those signs. Winning, what does it say? Fun is winning, or the advertisements for the gambling. They put right on there, winning, don't they? Right on there. Anyway, that's always I think that's very dishonest. But anyway, that they can do what they want, I guess. Anyway, so binomial. So today we're going to hone in specifically on binomial distributions. So what is binomial? What does bi suggest? Bicycle. Two. There's some kind of two thing going on here, right? You either win or you lose. There's going to be like two states. That's exactly it. We're going to hone in on distributions that particularly just have twos. Well, kind of like the one I did there, win or lose. All right, so let's take a look. So a binomial probability distribution has the following results. Fixed number there's four conditions. Fixed number of trials. The trials must be independent, meaning that the outcome of an individual trial doesn't affect the probability in the other trials. So, fixed number of trials. Trials must be independent. Examples will make it more clear. So I'll come back to these definitions. You don't really need to write these down. We'll talk about them. So 3 and 4. Number 3, there must be two categories. Like we talk binomial, that's the two thing. You either succeed or you fail. And the probability of success must be the same in all the trials. So let's look at an example. Example would be the best thing. Now they're getting into notation. All right, let me skip over that. Blah, 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 bunch of notation. We'll come back to it. Here's an example. Examples are always best, I think. So how about Twitter? Does everybody know what Twitter is? Honestly, I'm not 100% sure. I've never tweeted anything. So I'm probably one of those in the 15%. If somebody would grab me. They're saying when an adult is randomly selected, there's an 85% probability that this person knows what Twitter is. I think I'm probably in the I don't really exactly know category. Some kind of online thing where people give little messages back and forth. That's about all I know. So I'm probably in the unknowing 15%. All right, so I guess that's, according to Pew Research Center survey, 85% of adults. Probably all the kids know, right? But only 85% of adults. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. That's the question. Everybody checking the question there. What's the probability that exactly, and we're going to change that in a little bit. Instead of exactly, we'll say more than 3, less than 3, all kinds of things. But for now, exactly 3 of 5, 3 out of 5, know what Twitter is. Adults know what Twitter is. So you're going to grab 5 adults. What's the chance, if you know 85% of adults know what Twitter is, if you're going to go out and grab 5 adults at random, what's the chance that exactly 3 of them are going to know what Twitter is? Not 4 of them, not 5 of them, not 2 of them, not 1 of them, not none of them. But exactly 3 out of 5 know what Twitter is. How could you figure that out? Well, that is actually a binomial question. Because you see why it's binomial? You either know what Twitter is or you don't. Now, we could change this. We could change the question. You can do research however you want. They could change it and they could say, hey, we want to know how well do they know Twitter, and we want to rank them 1 to 10 or something, based on how often they've used Twitter, how often they read tweets, all that kind. We could do a ranking system, but that would no longer be binomial. You tracking with me? Is making sense? We're taking a question and breaking it into 2 states. They know or they don't know. Some things are not that way. Some things or the same thing, you could make it into, they know it super well, medium, or not well at all. 3 states. There's all kinds of ways to do it, but it's only binomial if you make it into 2 states. They know it or they don't know it. All right. So is this a binomial situation? Does it fit the 4 criteria? Yes. Let's go through it. First off, it's got a fixed number. So 5 times you're going to say, do you know, do you know, do you know? 5 different people. And they have, they're independent, right? One person knowing what Twitter is doesn't affect the other. It's called independent. There's 2 categories. They know it or they do not know it. In category 4, the probability is the same each time. Each person, the chance they know what Twitter is, 85% chance. So that's an example of a binomial experiment. All right. So how would we actually do the binomials? How do we actually figure this out? Well, they're going to go through this notation with N, X, P, and Q. Let me write out for you. You guys ready? Here come the note parts. So N is the number. We call it the number of trials, the number of times you're going to ask people, do you know what Twitter is? In this case, that's 5. We're going to ask 5 different people, do you know what Twitter is? 5 different adults, do you know what Twitter is? So N is the number of times you're going to try to get a yes or no response. X is the number that say yes, or we call it favorable responses or successes. The number of times we reach success. So what are we wanting? How many successes are we wanting? 3. Yeah, 3. In this case, we're wanting 3 out of 5 to say, yes, they know what Twitter is. P, what do you think P stands for? Probability. Yeah, what's the probability each time you ask? 85%. That's the 0.85. Now, here's the part that might be new for you. Q. P and Q are always the opposite when they're used in math and statistics and logic. P and Q are always the opposite. It's just how they always use it. So what's the opposite of 85% chance that they will know Twitter? 15%. Exactly. 15. You just do 1 minus the 85, and you get 15. That's the chance that they don't know what Twitter is. That's like saying there's an 85% chance of rain. What's the chance it's not going to rain? 15%. Right? It's just the rest of the percentage. That's what we always mean by Q. Really, we're not even going to use Q because we're just going to use our calculators. I'm going to show you how to crank this out. I was just reviewing it a half an hour ago because I forgot since I did the lecture a week or 2 ago. And this is all new to me. Like I said, I'm learning the TI thing with you. Last time I taught stats 15 years ago, we didn't have these. So I refreshed myself. So let's crank it out. So you guys have your TI calculator with you? We're doing something new. Like Eddie says, this is a lesson in itself, the TI. So we're doing the TI lesson part of the deal. It's exactly been the lesson for me. So on the TI, and if you have the Casio, connect. Who's the other person that already has the Casio? Oh, no. I know. You're helpless. All right. So hopefully there's a way. Just calling it like it is. All right, so on the TI, here's what you enter. You go to second vars, variables, and because right above it is the words DISTR for distribution, exactly. So you go on to the distribution menu. So you hit second. That button is in the sort of the upper right below the arrows. You know where the arrows are? See the button up there? So when you hit, clear that out. When you hit second var, you get distribution. You'll get on your screen a whole bunch of different distributions. We're going to be using a lot. Well, three of these. Three of these. Anyway, roll way down. We want one that's way down. Go down, down, down until you see the binomial. In fact, it's quicker to go over the top. If you want to roll over the top, you get there quicker. You go down to the bottom. You see there's a couple of there's a binomial PDF and a binomial CDF. Binom PDF, you find in that one? So just roll way down. Go way down on that menu. So after hitting second vars, get the distribution menu. Then go down, 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 down until you find binomial PDF. And that's the one we want. So make sure you're highlighted on the binomial PDF and hit enter. Hit enter. And it'll pop that on your main screen. It'll put BIN binom PDF. Okay, and then it's going to put a parenthesis. And I just wrote down a half an hour ago, reminding myself what goes in those parentheses. Are we ready?
No, wait. I'm confused right now.
So it looks like we're on track. Let's take a look. So here we go. Yeah, so the first thing is the, right here goes the number of trials. So how many times are we asking people about their Twitter knowledge? 5 times. Number of trials. Now for the 3 or 4 of you have the fancier calculators that just say number of trials. Super nice. Just put in 5. And next comes, what is it, probability?
0.85.
So that's the 0.85. Next comes what? What does it say? Values? Eddie, what does it say next in yours? Or Val, what does it say? May, what does it say?
3.
Oh, well, for the next one.
It says
Trials, probability, and then what's the next word?
X values or something. X something.
X values equals.
X equals, okay, great. X is, and that's like how many do we want to say?
Value.
3, right?
3, right? Yeah, exactly. 3, and I think that's it, right? Yeah, and that's it. Close the parentheses. Yeah, so if you have the fancier kind that actually show those words, when you then after you put those in, go down to paste, highlight the paste, and hit enter. If majority of you have like mine, like this, and you just hit enter. So when you're all done, just hit enter, and it'll give you an answer. And I don't know what that answer is. Let me do it. So what was it? 5, 0.85, 3. 0.138?
0.138.78.
Right, goes on and on. I don't know how many places they want us to round.
And as long as there's no percent symbol, they just leave it in decimal form.
Okay. So that's 13.8% basically, right? Is that making sense? So what does that mean? Real life. That means if you ask 5 people, this is the chance that when you ask 5 people, 5 adults, if they know what Twitter is or not, there's a 13.8% chance you'll get 3 of them, exactly 3 of them, out of 5, that'll say, yes, they know what Twitter is, and 2 that don't, given there's an 85% chance for each individual. Is that making sense?
That doesn't seem too complicated. You don't know what to do with the stuff.
Right, where to plug the things, huh? Questions I can answer on that.
Wait, so what exactly do we type in exactly?
Yeah, so it's this. It literally is that. So you actually find, you go to the binomial thing, you type in 5, comma, 0.85, comma 3. Oh, no, I'm just giving the names. It's just 5, comma, 0.85, comma 3.
Oh.
I'm just giving the names of the categories.
Second, and then hit large. And go down to
Yeah, I meant the heart.
binomial.
Yeah.
And the trials is going to be the
Other questions on that one? We good?
Five,
Okay.
the
Right. So, and skipping all these, we put all that in. There's the by hand way. Makes you thankful for your calculator, huh?
Actually, there's an easier way by hand.
Yeah, than doing this, huh? You're doing the C thing, huh? Nice. Combinations is way better. Yeah. It means like 5. I'm sorry, I'm joking around. You don't have to know. It means 5 times 4 times 3 times 2 times 1. It's called factorial. It means 5 all the way. Brian's got it better. If you have to, there's two or three of you doing it by hand, talk to Brian. He's got a great way. He's using something a little nicer than this that's easier to use. He'll help you out on that. Yeah?
So, is that answer Q?
No, that answer, here's the answer right here. 0.138. There's the answer we got, right? 0.138. And what it is the probability that if you talk to 5 people, you're going to get exactly 3 that say they know what Twitter is. 13.8% chance. So we answered their questions. Does that make sense? No, I appreciate it. That's the important thing. Are we making this? That's really the most valuable thing, honestly, is that this makes sense to you. Because real life, you're probably not going to do a lot of statistics calculating, but you might read a study. And it's got to make sense to you. That's how you would be an intelligent user of stats in the real world. You know, what does it really mean? Does that make sense? That's probably most valuable. Right.
The hardest part of stats, it's not the formulas. It's interpreting what the data means.
Yeah. Right.
No, not even the words. It's interpreting what your results are telling you.
Yeah. So see what it says here? The probability of getting exactly 3 adults who know Twitter among 5. So if you grab 5, you go up and just grab a group of 5. The chance that 3 of them are going to know what Twitter is 13.8%. That exactly 3 will know. Given the chance that each person has an 85% chance alone, the chance that 3 out of 5 will know is 13.8%. All right, let's move on. So yeah, there's the formula. Brian's got a better way if you want to do it by hand. And we use technology. There's the technology we're using, the TI. We didn't do it exactly that way, but you could. That's how yours ended up looking, right, on the Casio. Yeah. All right, it's all good. Here's the one I've been wanting to do. I like this one. This is the NFL overtime rule. Let's use what we're learning to answer a real-life question. I don't know if you're like me. I enjoy watching football. I never played football. I would have gotten hurt, I'm sure. But I enjoy watching football. And I always think the overtime rule is cheating. It always irritates me. Because I always think that's not fair. Whoever wins the coin toss has a better chance of winning. That's just making it unfair. That's like saying, hey, we're going to have a boxing match today, but before the boxing match starts, we're going to flip a coin. Whoever wins the coin, whoever loses the coin toss, has to have both hands tied behind their back. And then we'll do the rest of the boxing match. Well, the coin toss is pretty much going to decide the boxing match, right? That's my feeling of the overtime coin flip rule, right? When a football game comes down to the overtime, they go out there and they flip the coin. Tom Brady always wins the coin flip. I don't know how he does that. Anyway, so,
Late in the quarter.
that's right. But is that true or not, though? So is what I'm saying have fact behind it or not? How would you go about investigating, whether that's true? Because everybody has their theories. I had a friend at another college, and he used to say, he was one of the people that worked there, and he always swore that the whole NFL was rigged. That all the players got together and they agreed on who was going to win the Super Bowl that year. That seems nuts to me. But anyway, I don't think that's any way that
The
would
refs
be.
decided that one last game. That's how the Rams ended up going to the Super Bowl.
Yeah, the refs had an input on that. But as far as all the players agreeing to let one team win, he really thought he swore by it. And I'm like, I think they really want to win. I don't think it's crazy. Anyway, so maybe I'm crazy too. Maybe my little complaints about the overtime thing is crazy. How would you determine whether there's some fact behind it? That's what we're doing here in stats, right? We're trying to learn when does data so strong that it's beyond luck. It's beyond, you can always believe it's luck. You can believe anything is luck if you want. But is it reasonable? At some point, it doesn't become reasonable anymore, right? And that's what we're doing with stats. How can we use the stats to determine if the overtime rule is really biasing things. Well, here's what you do. You just take all the data from 1974 to 2011. 460 NFL football games went to overtime in those years. And 252 of them were won by the team that won the overtime coin toss. You tracking with me? 252. Now, is that more than half? I think it is. Somebody have a calculator? What is 250? Well, it should have been 230, right? Isn't that half of 460? Should have been 230. If exactly half the teams were winning, if exactly half the teams who won the coin toss won the game, it'd be 230. You tracking with me? So we would expect 230 of the ones who won the coin toss to win the game if the coin toss was making no difference. Am I making sense? Right? Because you don't want the coin toss helping out. You want fair competition. Right? That's the whole point. And you don't want a coin toss to get in there. You know, we won because of the coin toss. Well, that's kind of lame. Right? You don't want the coin toss determining results. Well, how do you know if it is? Well, if it's not, if the coin toss is not making a difference, which is what you want, then shouldn't it be the case that those who won the coin toss still only won half the time? They're just all random teams. But more than half are winning, aren't they? Yeah, but that could have just been luck. Could it or could it not? That's what we're going to examine now. Does the question make sense for stuff? Wouldn't we expect exactly half of the teams who won the coin toss to win the game? If the coin toss is not making a difference, that would be 230 out of the 460. But in reality, more than half. Right? 252 of the teams who won the coin toss won it, right? So, won by the team that won the overtime coin toss. Yeah. So 252 coin toss winners won the game instead of exactly half. Now that's more than half, but somebody could go, yeah, but that's just a few. That's just, I mean, it's a lot of games. That's just, that's close. That's only what is that, 22 more than half? That's only 22 more than half. Right? 230 is what you would think. That'd be half the teams. It's only 252. That's only 22 more than half. What's 22? That's like a small part of 460. I don't know what the percentage is, but small. Or is it small? How do you determine that kind of thing? You guys know enough probability right now to bring in a very intelligent answer to this question. So how do we know? Is the fact that 22 more than we would expect, 22 more than half, one who won the coin toss, won the game, is that significant? Is that beyond reasonable luck? Of course it could be luck. Anything could be luck. But is it reasonable? Is it logical? Is it reasonable to think it's luck? Or is it more reasonable to think the coin toss winners have an advantage? That's probably not luck. And what's the line we use for luck? 5%. Right? If we calculate this out, and there's less than a 5% chance that it was just raw luck, because it always could be luck. But what's the chance of that? If there's less than a 5% chance of luck, then I'm not going to believe it's luck. You can believe it's luck if you want to. You can believe anything you want to. But I don't think you're reasonable. I don't think it's reasonable to believe it's just luck when the chance of luck is so low. So that's the question. Is there less than a 5% chance, excuse me, that it's just luck? Well, how would you determine that? Do you see, this is binomial. This is a binomial question. It's just, right? We're saying, what's the chance if you have 460 games? What's the problem? Now, let's assume, what's that, Val?
Those will be trials, right?
Those will be our trials, exactly. That's going to be our 460 trials. And let's assume the coin toss is making no difference at all, right? That's what we're assuming. Coin toss doesn't help. And see if we get something that says otherwise. So we'll assume the coin toss doesn't help. If the coin toss doesn't really help, then what's the chance? If you're the team that wins the coin toss, what's the chance you're going to win the game if the coin toss is not helping? Well, 50%, right? We're assuming it's a 50% deal. Let's assume 50% of the teams should have won. Right? These are just all random teams. Right? Yeah, but how do you know if it's a better or worse? Yeah, there's a lot of better and worse teams. We're just saying out of 460 games, there's so many different games. Half of the teams it should have been evenly distributed. If the coin toss is making no difference, you should have had just as many winning who won the coin toss as those who lost the coin toss. 230, 230 is what it should have been. So what's the probability? The question is, what's the probability in 460 trials where the chance each time is 0.5, the chance the coin toss winner will win the game, 50%.
So the value is going to be x values 2.
And what's the chance that x is actually what? What do we want here? Greater than or equal to 252. Because that's what actually came out. It's like going and you're going to show up at 460 games. The chance the coin toss winner wins each game is 50%, right? Does everybody understand why we're doing the 50% thing? Right? Because you might say, well, no, it's not 50%. The teams aren't evenly matched. No, that's not what we're saying. We're saying whoever won the coin toss, right? One of those two teams is going to win the game, right? What's the chance? And the coin is just 50-50 flipping. So the chance that the coin toss winner happens to be the game winner, that should be 50-50, shouldn't it? Am I making some sense here? Even if you say, no, but what if one's way better than the other? Yeah, sure, okay, one's way better than the other. But I'm still going to flip the coin.
Still a 50-50 chance.
It's still 50-50 that the coin ends up being on the better one or the worse one. It's 50-50. We're just flipping a coin. 50-50 chance that the coin ends up being for the winner rather than the loser, right? And so we're saying, what's the chance that 252 or more times that the coin ends up being on the winner? Because it should only end up there 50% of the time if there's no real difference being made by the coin. So that's the probability we're examining. We're going to do a probability thing. But this one's different now because it's not equal, it's greater than or equal. So that's the part, and that's the whole issue through the homework. So let me make that clear now. So when you do the binom, so this is the tricky part of using the binomial thing. Everybody tracking with me? The binom PDF is only for x equals a number. That's like the last problem we just did. What was it? We wanted x equals 3, didn't we? Yeah, right there. X is 3. Remember the last problem we just did? We used x equals 3. So for PDF, probability distribution, that's when they said exactly 3 out of 5 adults know what Twitter is, right? But if they had said to us, what's the probability that 3 or more, that's really a more typical question, huh? What's the probability that 3 or more will know what Twitter is? That, whenever they say or more or less, you got to use the CDF. CDF. Let's go back here. I'll write that out for you. Whoop, I lost it completely. There it is. So PDF is for equals, and binom CDF is for, actually it's for less than or equals, and we'll change it to be greater than. So I want to camp here for just a minute and make sure we're all clear, because this is and we'll do 5 to 10 problems where we'll do this again and again and again, so you'll get more and more the hang of it. But here's the main idea. PDF is just for equals. CDF is for less than or equal. C stands for cumulative. Do you know what I mean? If something accumulates, it builds up, right? So this is the binomial cumulative distribution function. They're accumulating, they're building up. They're not just one number, they're not just 3. It's 0, 1, 2, or 3. Does that make sense? They're piling up on their way up to 3. Cumulative. So it's for less than or equal to. Now, the real trick on this problem is we don't want less than or equal to. Look up here. What do we want? We want greater than or equal to. So that means you have to tweak your CDF function. And this will be the hardest part of using this, like Brian was saying, is reading those words and figuring out what you have to do to get the calculator to give you what you need in the real world. So think with me. What if I said, hey, what's the chance that the number of winners is going to be greater than or equal to 252? That's what we're trying to figure out. What's the opposite of that? If I said greater than or equal to 252, the opposite, and somebody said no. If I said, hey, what is it? How many people showed up at the party? Was it greater than or equal to 252? And somebody said no. What does that mean? What's the opposite of being greater than or equal to 252? It's being less than 252, right? Nuruddin?
I was gonna ask, would we subtract that 252 from the 460?
No. I'll explain. Less than 252, that's true. But rather than less than, remember what we need to do, that's a true statement, but we need to write it as less than or equal to, don't I? So what is it less than or equal to? If somebody said, did the number of people that showed up, is it greater than, bigger than, or equal to 252? No, the opposite is less than or equal to what? 251. You tracking with me? If 252 or more came, the opposite of that would be 251 or less. Are you tracking with me? Let me pause there for a minute. This is what we're going to do again and again and again and again on these problems. So we're trying to figure out 252 or more. The opposite of that is 251 or less. Isn't it?
Would that be Q or no?
No, we're not going to need to do anything with Q. Those of us who use the calculators, Q, don't even need to ever use Q. So, but I know it seems similar, huh? Because it is opposite, but it's opposite probability instead of number. Yeah, forget about Q. It's just going to confuse the issue. Does that make any sense? So the opposite of 252 or more is 251 or less, isn't it? So if 252 or more wins, the opposite would be 251 or less. So now why am I doing all this? Because your calculator can only do less than or equal to. It can't do more. And I want to answer a more question. So I do it by doing the opposite. I have to. Is that making sense? So the way we answer a greater than question is always by doing the opposite less than question. Because that's all our calculator can do. And so we'll do several of these, but let me give you that main idea again. Whenever you want to answer a let me re-say it this way. All your calculator can do is equals for PDF or less than or equal for CDF.
What CDI stand for?
Cumulative. So they accumulate up to that point. So all your calculator can do is equals for PDF, binomial PDF, or less than or equal for binomial CDF. So therefore, if you want to do a greater than question, you have to answer the opposite, less than question, and then take 1 minus it. Like chance of rain is 80%, chance of no rain is 20%, right? Just do the opposite in the end. So I'm going to answer this question on my calculator right now, less than or equal to 251. I'm going to get that answer, but that's actually the opposite of my question. When I get that answer, say it comes out 20% or whatever, then I'll know the real answer is 80%. 1 minus it.
That's what I was going to ask. If it was just a 1 minus kind of a...
Yeah, I just do the 1 minus thing. Is that making sense? So whenever they give you a greater question, you answer the less question and then take the opposite at the end. Take 1 minus the final answer. Just like chance of rain is 20%, so the chance it's not going to rain. You know, if I say, hey, what's the chance it's going to rain? Somebody said 20%. And I go, oh, no, I meant what's the chance it's not going to rain? Then 80%. That's what we're doing. We're doing the opposite at the end. Because we want a greater question, and our calculator can only do less. So we do less, and then take 1 minus the answer. So let's do it. So let's have our calculator using the binomial CDF calculate for us. What's the chance, calculator, that doing this coin flip thing, that there would be 251 or less winners of the game who won the coin flip? Let's figure that out. So I'm going to type into my calculator now, binomial CDF. Let me have some room here. Yeah. So I'm going to type in my calculator. Binom CDF. And what's the first number is trials? 460. 460 different games. And then the next number is probability. 0.5. Chance that the coin flip winner would end up being the game winners. Should be 50% if it's really not affecting it. And then we want, the next number is since I'm doing CDF, it's the less than or equal to number, which is the 251? What was it? I forgot already. 251. You're right. I'm messing up. 251. Parenthesis, enter. Is that making sense? So let's do that together. PDF.
percentage?
No? I don't think I'm doing it wrong. Oh, wait a minute.
0.97.
Oh, wait, I did the wrong thing. I messed up my calculator.
So would it be 0.0224?
Yeah.
Is that what you guys getting?
Minus 0.977.
Yeah. I got 0.997, or no, sorry, 977. Yeah.
57.
Right.
628.
Yeah, so I'll just go 6 places is plenty.
And then you go 1 minus.
And 1 minus it. Did everybody getting that though so far in their calculator? Did you putting in binomial CDF, 460 trials, half chance, and less or equal to 251. That's the opposite of our real question. Getting that okay?
Why did you say earlier -1 is the opposite? You get the minus
Oh,
one.
no. And now, because,
1 minus.
yeah.
977.
Now we take 1 minus.
You
Take 1 minus 0.022429. Is it 29?
So that's the final answer? Whatever the one,
Yeah.
1 minus
Fine.
0.999.
Yeah.
4,
89.
2. Yeah, I'm just going to round it.
Less than 5%?
It is.
So that's just luck?
That's the chance it's luck. But is everybody caught up here? I don't want to race it until we draw a conclusion.
So that's significant.
Yeah, that can't be luck. I guess anything could be luck, but it's not reasonable. In other words, if that coin toss really is not making a difference, then the chance that you would have this many more winners that happen to also be the coin toss winners, there's only a 2% chance that would happen. That's not going to happen unless the coin toss is making a difference. And the NFL knows this. That's why they've been trying to fiddle with the rule, because the coin toss is affecting the outcome of the game. And we got statistical evidence for it.
That's why they said now if you score, you still have a chance.
Yeah, they changed the rule because they tried to improve it. Yeah.
Oh, they did? I thought it was.
So,
It used to be for a long
It used to
time.
be end right there. As soon as the first score,
That was the old rule.
but if you score, they get a chance to score.
So it's like
back.
Unless you score a touchdown.
Yeah.
It's automatically over. If you get a field goal, they get
Then they
to.
get a chance.
Yeah, I still think it's unfair. New data will be coming in, but
I
they're trying to improve it.
Quarter out until they they just play till like the whole quarter.
Yeah, they're afraid of injuries and all that, so they're trying to balance.
Or the NCAA can do it.
They go for the 25-yard line or whatever. Yeah, that seems. I think the NCAA rules a little bit better. Yeah, they have and they switch. I don't know if you know what the NCAA is.
Yeah.
So they do a coin toss still, but the way they try to get the coin toss to take, I think they're masters in the way they thought it out. They have whoever wins the coin toss. There was a really big game. What was it last year where they went 2 or 3 times back and forth with who was it? My buddy's team. He loves Georgia. It wasn't this year. It was the year before. Georgia was in a. Yeah, I think it was in Oklahoma, Georgia, and they did like 2 or 3 of the overtimes back and forth, and that's when I really saw the rule played out. I didn't realize it. So whoever wins the coin toss starts out at the 25-yard line, and they can either get a field goal or a touchdown or nothing. Then the other team has their chance, but that seems like it's better to go second, which it is. Everybody knows. Because if they got a field goal, all right, well, we need to go for the touchdown, or they didn't do anything, we can just get a field goal. Yeah, but then the way they try to fix that is they go, if you get the same thing as them, because that's what happened in the Oklahoma-Georgia game 2 years ago, is it was like field goal, or touchdown, I can't remember. They both got the same thing, and then they swap it. Whoever went first the first time now goes second. And so then all of a sudden Georgia had the advantage, because then they were going second. I thought, that's well done. They thought that out. So they're trying to take the coin flip out of it. That's the whole point, coin flips. Otherwise, let's just go out there, line up the teams, flip a coin, heads, all right. Patriots won again. Heads, that'd be dumb, right? We don't want the coin flip determining the results. So this is strong statistical evidence that what this says is if the coin flip really was making no difference, you should have about the same amount winning, but in reality we have more winning who won the coin flip, and it's so many more that the chance that's just luck, it could be luck, but the chance it's luck is only 2%. It would be very unlikely to have that many winning who won the coin flip if it wasn't making a difference. There'd only be a 2% chance of that. So it's not reasonable to believe it's just luck. The coin flip was affecting the outcome. Does that make sense how to do the CDF thing? Is everybody good? So the CDF just does less than or equal. So sometimes they will ask us a less than question. So then we just do the CDF and that's our answer. But sometimes they'll ask us a greater question, like this one. They asked us greater than or equal to 252. So we have to take our answer and do 1 minus at the end, do the opposite. Questions? We good on that one? Is that, you're informed now. You can talk intelligently about math and the NFL coin flip. Of course, it's old history now. They've changed it already. But new data will be coming out in the new rule. I still think it's somewhat unfair. All right. All right, so let's come into this part. So, oh yeah, we did that. We're basically done. Let's go to the homework. So on to the homework we go. All right, based on a survey, assume that 43%, here's question number 1 from your homework. Assume that 43% of consumers are comfortable having drones deliver their purchases. You know, that's the new thing, right? That's where we're going, right? Amazon's taking over the world. And basically they're just going to have warehouses, giant warehouses in all the cities. And whatever you order, it'll be there in 2 hours. Because a drone will fly it to your house, right? That's what they want to do. I don't know if you've heard. That is the desire. To have drones sitting in warehouses that fly stuff to your house. Immediate delivery. There will be no more local Target at all in 20 years maybe. I don't know. And I'm not sure that's good. But anyway, it just seems like where we're going. So, but is everybody comfortable with drones flying to your house to deliver your stuff? Some are not, for some good reasons, I'm sure. So let's suppose that 43% of consumers are comfortable with the drones delivering their purchases. Then we'll have people trying to grab the drones halfway through flight to steal the stuff, like they do off your front porch now, right? It's funny how technology and people try to battle against it. All right, suppose that we want to find the probability that when 5 consumers, this is what Amazon would wonder, are randomly selected, exactly 3 of them are comfortable with delivery by drones. So this is just a warm-up question. They're just making sure we understand the basics. What would be the value of n in that case?
N would be 5.
Yeah, 5 is the number of trials. Everybody good with that? N's the number of trials. We're asking 5 consumers, so that's n. What's the value of x?
3.
Yeah, that's our x, 3. We want 3 of the 5. It's just like the Twitter question, huh? 3 out of 5 to be comfortable with the drones delivering their goods. What's the value of p, the probability?
0.43.
That's the 43% chance that a consumer is happy with the drones. And q?
0.2583.
It's 1 minus 0.43. No, Q's just the. We're not even gonna answer this question really. They're just wanting us to set up. We don't even need to do the binomial thing on our calculator. That's what I mean. Just 1 minus. That's like rain, no rain. P and Q are opposite, so that's going to come out 0.57. Yeah, Q is the opposite of P. It's the 1 minus. We don't even need to use Q for our calculators. It's just something the by-hand people have to deal with. Is that making sense? Number 2. I'll move on if you're good. Number 2. Determine whether this is binomial or not. Okay, suppose treating 100 men with a special shampoo and recording yes if they experience any burning or no otherwise. So what if somebody sets up an experiment where we give 100 men this shampoo, they put it on, and they say, yes, I experienced burning, or no, I did not. Is that a binomial experiment? Yeah? It's a yes, no. Now, if they instead say, hey, rate how you like it, 1 through 10, that wouldn't be binomial, huh? See how the same experiment can be set up to be binomial or not? They say, just tell us, rate the shampoo 1 through 10. Well, that wouldn't be binomial anymore. But rate whether it felt burning on your scalp. Yes or no, that's binomial. So our answer would be yes. It's binomial. All 4 requirements, I'm not going to go through them, are met.
Yeah, that was a different question.
Yeah, it changes them. Number 3.
That one was easier.
An experimental drug is administered to 170 randomly selected individuals with the number of individuals responding favorably recorded. So if you give this drug, the number that respond favorably, they have a good response. They do well. They get over their sickness or whatever. So is that binomial? Yes. Because now they respond favorably or they don't. It's just 2 conditions, huh? Favorable or not. So that's 2 conditions. Yes, that's binomial. On we go. Number 4. 3 cards are selected from a deck of 52 without replacement, the number of sevens is recorded. Is that binomial? It's a tricky one. It's actually no.
Each one, each probability is different.
Yeah. How do you know? You're just thinking it out?
You're just picking random.
Good thinking. Yeah, you're right. You're totally right. Ken, right? Yeah, you're totally right, Ken. Good thinking. Yeah, I don't know if you ever, I grew up with my family playing cards and all this stuff, so I thought this way since I was really young, but the probabilities change when certain cards come out of a deck, right? Like how many sevens are in the deck? 4 sevens. I don't know if you ever play cards. 4 sevens, right? Kings, hearts, diamonds, clubs, and spades, right? For sevens. So there's 4 sevens. But once you take a 7 out of the deck, then there's only 3 left, so the chance of getting a 7 is lower. So you see, the reason this is not really binomial is because the probability is going to change each time, right? If you're just reaching into the deck saying, I really want to get a 7, what's my chance of getting a 7? You reach in, you grab. If it's not a 7, then you're going to reach in the second time. Is the chance, if the first one was not a 7, the second time you reach into the deck, is the chance higher or lower that you're going to get a 7? It's actually higher. Because now there's just as many 7s, and there's less possible cards. There's only 51 cards now. Anyway, whatever, it changes. We don't need to do a big probability thing. It changes. Brian.
Okay, so you draw the first card. It's a 7. You don't replace it, so there's less 7s.
Now it goes down. Yeah, so I said the first card was not a 7. And so if the first was not a 7, it probably goes up. If the first was a 7, it goes way down.
Now,
it changes
with
way down.
replacement, though, then it has the same probability.
Yeah, if you were putting it back in the deck and reshuffling the deck every time, then it would be same probability every time. Yeah.
Yeah, that one is, it's kind of tricky because of the fact that, oh, wait a minute, there's only 4 7s in the deck, so.
Right.
But because of the fact it says without replacement, that changes.
Brian's right on the money. Yeah, I should emphasize that word. Without replacement, meaning you're not putting the card back and reshuffling the deck. So you're changing the deck every time, right? When you take a card out, what's in there now is different.
So it'll be D?
So the probability is different. Yeah, no, because the trials are not independent. The probability of success differs from trial to trial. Exactly. Changes each time. You guys ever played, it reminds me of the game, Exploding Kittens? We play a lot of games in my house. You played that game?
What?
It is hilarious. And
Yeah, someone like was, buy this game.
it's like a party game. A lot of people played it. Yeah. It's totally fun.
Floating kittens?
Basically, yeah, I mean, it's goofy. It shows these kitties blowing. Sorry if you love cats, but it shows kittens blowing up. It's mocking kitties. Anyway, but it's like this probability. It reminds me of the probability. Because basically the whole game is to not draw the bomb. And so if you draw a bomb, boom, you just blow up. And so anyway, it's a fun little card. But it makes people that are more anxious get really uptight in the game. It's just kind of funny to watch them. Because as it comes around to your turn to draw and nobody else got the bomb, it's like, I don't want to. They get like all freaky about, because boom, you're done, you're out. If you get the, anyway, it's a very fun game, I think. Exploding Kittens. Try it out. Very fun party game. All right, so number 5. Now this question, honestly,
Love spades.
number 5, I don't really, I don't agree with the answer. I'm probably wrong, but I don't know. What are you going to do? It says 600 different voters, two political parties. So you grab 600 out of 8,500, and you ask them if they like Party A or Party B, or Party A, yes or no. So anyway, that seems binomial to me, but they say it's not binomial. So, because you're grabbing 600 people out of 8,500. And, well, no, they're right. Okay, I guess it's like the card thing, huh? Yeah, to me it's really picky. But they're technically right. It's like the card thing. Once you grab, you have this 8,500 people, 8,500 people. You're going to ask 600 of them if they're a member of political party A, yes or no. So it's binomial in that sense. It's yes or no. I'm in that party. I'm not. Yes or no. But the reason it's technically not really fitting the 4 conditions of binomial is because it's just like the card thing. Once you have a group of 8,500 people, right? Some amount of them are in the political party. Some are not. It's just like 7s. Some amount of this deck is 7s. Once you start selecting out of that deck, you're changing the probability. Right? Get the idea? So it's pretty picky, I think. But technically, you can tell I'm not going to put that on the test. That's really picky. But technically, yeah, we're changing the deck.
So the number of trials are not fixed.
I think it's going to be.
No,
They're
the
not
number of trials are
independent.
fixed.
It's the D. Yeah, they're not independent again. Meaning they're not the same problem. It matters. Once you start selecting out of the deck, it changes the chance you're going to get a 7, or it changes the chance you're going to get somebody in that political party because there's less left or more left or whatever. It changes. The 5% rule, basically, they have a rule of thumb. I just don't want to give you too many details, overwhelm you. So I'm not going to test you on this. But if you're wondering why they said the 5%, it's not the other 5%, which for significance that we use sometimes. I guess it kind of is. Basically, it means if this 600 was less than 5% of the whole pool, then you can ignore the change. It's so small. But if it's more than 5%, and it is, 600 is more than 5% of 8,500. So that's the reason it's an issue. So anyway, I'm not gonna push you that hard. Let's go to number 6. Okay, so now we're enough with that stuff. Here come the regular questions. This is more the regular stuff. We're going to use our calculator, the binomial, PDF, CDF buttons. Let's practice getting comfortable with that. Assume that when adults use with smartphones around, say 60% of them use them in meetings or classes. If 5 adults are randomly selected, find the probability exactly 3 use their smartphone in meetings or classes. So can we do this? That's an actual question. Is it going to be? So they're saying exactly 3. Is it going to be a binomial PDF or a binomial CDF?
PDF.
Good. Yeah, you getting the hang of it? Because the PDF is always for equals, huh? And the CDF is cumulative. It's for when it's less than or equal, actually. So let's do the PDF. So we're going to do binom PDF. And we're going to put in the numbers in our calculator. What's the number of trials? Which is 5, right? Just 5. And the probability, you put that next, 0.63 and 3, hit the equals button. Somebody getting an answer?
0.34234143.
All right, 0.342. Oh, they want 4. What was it again? Sorry, Val, I cut off too quick.
0.342314.
So they want 4 places, so 3, 4, 2, 3. Rounded to 4 places. So it's not CDF, it was PDF on that one. We good there? Anybody else getting that same answer? No? Want me to do it?
No, I did my homework, so I did it all based on my homework.
46, 25.
I'll double check. So 5. You don't even have to put the last parenthesis, by the way. Yeah, that's what I got too. That good? We all good with that? Let's try number 2. Adult smartphones around 42%, blah, blah, blah. 25, randomly selected, find the probability exactly 19. That's the same thing. How about we move on? There's harder ones. I want to get to the harder ones.
Do 8.
Yeah.
So
So it's the
number
same
8.
thing.
Yeah, let's do number 8. 44% use me about 5 adults, at least 2. Yeah, good. That'll be yeah, nerdy.
Oh, no, I was just saying I figured out how.
You got the answer for number 7 already?
Not the answer, I just figured out how to do, like, how to plug it in.
Number 7 or number 8?
Number 8.
Yeah, number 8. Yeah, let me give everybody a chance first off. Think about what you're going to do.
5,
Uh-huh.
comma, 0.44,
Right.
and 1. Yeah. And then, once you get that answer, it'll be 1 minus what that answer.
Beautiful. Exactly. Yeah, let's think it out. Let's see how he arrived at that conclusion. So this is the main tricky part. So at least 2. So remember now, we're going to do CDF, and CDF, the way they set it up on your calculator, means less than or equal to. So you've always got to take their question and change it to less than or equal to, because that's what your calculator could do, right? So they're saying at least 2. So at least 2.
So the trial is not, or on this one, the trial is 5.
Yeah, that's going to be 5, and yeah, that part's all the same. Yeah,
Its value is 6.
5. 5. Yeah, it's 5. Asking 5 adults. Maybe you have a different one, Eddie. Do you have the same one as me?
Trials, right?
What? That's number of trials is 5.
And the P is the
.44.
44.
Yeah, so we'll do.
X value would be
Yeah, let's put that in. Binom CDF. So the number of trials is 5. The probability is 0.44. But the hard part is always the X.
so that's what 1.
Yeah, and let's talk about Y. Let's talk about y. It is 1. So, everybody with me? This is the part I really want you to get. Whenever, remember your CDF automatically does less than or equal to. It always does less than or equal to. So if you want to do at least 2, what does that mean? Let me just write it out. Doesn't it mean 2, 3, 4, on you go, right? At least 2 means 2 or more. So what's the opposite of that? 1 or less, huh? That's why we do 1 here. Does everybody see that? And then when you get your answer, you got to do the 1 minus, like Nerdy was saying.
1 minus the answer then?
Yeah. But does everybody see how that's the opposite of at least 2, which is 2 or more? The opposite is 1 or less, huh? Less than or equal to 1. See how that's the opposite? So we're doing the opposite. Whatever answer you get, then you got to subtract from 1. So
1271432.
what it is.
1 minus that is 6.7285.
Yeah, right. 0.2714. And then we got to take 1 minus that.
7285.
Yeah. So then 1 minus 0.2714 is 0.7286. 0.7286, y'all getting that? That's the final answer.
Oh, yeah.
How we doing? Yeah.
So ours says at least 8,
So we're good with that one. Let's go on to what's number 7 say? So I'll just try to do ones that are different now. Oh, exact. Okay, so you just tell me on number 7, exactly 19? What's exactly 19? We're going to do, that's just a PDF, huh? Can I just skip that one? That one's just a PDF. It's only the greater or less that are hard, right? On to number 8 we go. Number 8, at least 2. At least 2. So remember now, CDF, so we're going to do a CDF. It's not exactly, so it's going to be a CDF. And what does CDF do naturally? It does less than or equal, doesn't it? So the binom CDF, it's going to be whatever. How many adults? 5? 5 adults, 0.44. That part we know. Whatever you put here, remember, is less than or equal. The calculator understands it as less than or equal to. So you have to kind of speak the calculator's language and be the translator to translate the problem into the calculator's language. So that's real life using technology. So at least 2, try to be as real with this as you can. That's always the most helpful thing, is try to be real. Real, real, real. So what does at least 2 mean? Just think about if I say in my pocket, I've got at least 2 coins. If I said I've got at least 2 coins, then I've got 2 or 3 or 4 or more, right? That's at least 2, isn't it? Right? It's 2. At the lowest, at the least 2. Maybe more. 2 or 3 or 4, etc. That's what at least 2 means, right? So, but I have to do less than. That's all CDF does. So I gotta have to do the opposite on this one, aren't I? So notice for less questions, we always do the opposite. No, I said that backwards. For greater questions, we always have to do the opposite because the calculator only does less. So anyway, so what's the opposite then of 2 or more? 1 or less, right? Isn't that the opposite? The opposite of having 2, 3, 4, etc. coins is having 1 or 0, isn't it? 1 or less. So that means we put in 1 here, and when you get, and now let me show you a quick way, guys. When you hit enter, everybody watch for a second. This will save you some time. When you hit enter and you know when you're going to have to do the opposite, you can just go 1 minus and hit second and the answer button, which is down at the negative on the bottom of your keyboard. If because you don't want to type it in, round it, type it back in, write it down. Just hit 1 minus second answer. You guys know I have an answer button. It's above the negative key at the very bottom of the calculator. And it'll just grab your previous answer, save you some time. So 1 minus second answer, enter. On that, Ken.
I have a question.
Yeah.
How do you do it? 20 adults are random selected.
Okay, we'll get there. What number is that?
Number 10.
Okay, we'll get there in a second. Let's finish this one up. Is everybody good with that then? So how do you know, let me ask you, how do you know when you're going to do opposite? What kind of questions do we need to do the 1 minus opposite thing at the end? Any that are at least or greater, right? Any greater, because the CDF function only does less than or equal, right? We good? All right, number 9. Yeah, let's do number 9 together. That one's a good one. And then we'll do 10. Fewer than 4. Fewer than 4.
Just plus that's the
All right.
and then just 4 or less.
Careful.
3 or less.
Yeah. Right. So binom CDF. So here again, so think with me. We've got to speak the calculator's language, but translate the word problem into his language. So binom CDF, right? Because it's not equals, right? It's not exactly. Fewer than 4. So what is this? 15? 15 adults. Probability is 0.49. Okay, now what am I going to put there? Well, remember, the calculator does less than or equal. Less than or equal. Try to be as real with this as you can. Really, that especially on word problems, that's really... If somebody's asked me after all these years of teaching math...
So fewer than would be less than, right? So then that would be the same number?
Right.
So you do the same number.
Yeah, so what's it going to be? What if I said fewer than 4 people were there? Fewer than 4. How could I change that into less than or equal? Less than or equal to 3. Does that make sense? Because isn't 0, 1, 2, 3, aren't those all the numbers fewer than 4?
Yeah.
Does that make sense? Everybody down there with me here? This is the kind of stuff that tricks people right here. Are you with me on that? So if I said fewer than 4 people, if somebody said, well, who was there? Well, there were fewer than 4 people there. What does that mean? 3 or 2 or 1 or 0. We put 3 there. Because why? Because that's all the CDF function can handle. It's less than or equal. That's all it speaks. So you got to change whatever into its language.
But we're not doing the 1 minus thing because...
Right. Because this is not the opposite, is it?
Wait, what?
This isn't a greater, is it? It's not a greater question. It's only the greater ones we do the opposite. Right? This is not the opposite of fewer than 4. It's the true meaning of fewer than 4. So it's just that. No 1 minus on this one.
Oh my goodness.
How we doing? Does that make sense? Let me go back. Everybody see on number 8. Let's compare. Look at number 8.
Lesson, you do the fewer lesson.
So the CDF does less. So if you're doing less, no need to do the opposite.
Fewer or less. Those 2 words I need to see.
Yeah, they can give you lots of words. I can't pin it down. Anything, because they could say does not exceed, fewer than, shy of. There's a million words they could say. Anything that logically means less.
These are using
Oh my
exactly
goodness.
fewer than or less than or
Fewer, less, smaller, tinier, no more. No more than. Yeah, see, there's just a million ways they could do it. So yeah, so don't try to pin yourself to certain words. Pin yourself to the logical idea. Anything that logically means less. There's a million words they could use to say that. Anything that means less, we don't do the 1 minus because that's what the CDF does.
when they use the word at least, that's when we subtract.
Well, anything that means greater. They don't have to use at least. All right. So let me write something out for you. Let me write something that'll help. So binom CDF again means less than or equal to, right? Means less than or equal to. So if the question is less, now I just say less or fewer or smaller, or, no more than, blah, blah, blah. I can't pin it to certain words. Throughout this course, they're going to use all kinds of different words. That's what they do in a college level course. They mean for you to gain a quantitative vocabulary. A vocabulary that can read words like that and know what it means. And that's a lot of the challenge. So you have to learn, and you can, just takes time, practicing those words. There's a million words they could use that mean less than. And so if they say words that mean less than, then there's no need for 1 minus the answer. It's not needed. But if the question is greater, or at least, or more than, or anything like that, then 1 minus the answer, because that's the opposite. That's the opposite. So everybody see those conditions. So case 1, case 2. So the binomial means less than. The binomial is CDF. Means less than or equal to. So if they give you some kind of question that's consistent with that, it's less, then there's no need for the opposite. No need, because it's not the opposite. It's the same. That makes sense? There's no need to do the opposite, because less is not the opposite of less than or equal to. It's the same.
So
But-
if we do CDF, then we don't have to do 1 minus the answer.
Did you have
Is that what you're saying?
I'm sorry, I wasn't listening.
So if,
I was posing for the picture. Did you want me in that picture, or
So you just.
did you? I'm just joking. I'm sorry, I was just joking.
Yeah.
so when the binomial states, when we have to do the formula binomial CDF, we do not have to do the 1 minus the answer. Is that what you're saying?
For when?
For, because we do the CDF when it comes to the wording less, fewer, smaller.
Yeah.
So that's only when we use the CDF binomial, correct?
See, you have to do greater too. You can do greater.
Greater
Right.
is the
You do
PDF, right?
PDF, no, PDF is equal to.
PDF was equal to.
Equal or exactly.
Is that-
Yeah, PDF was
Right.
exactly.
So
we-
exactly,
we
Both
do the
of these
one.
are
greater or
CDF.
lesser is CDF.
Yeah, both of these are for CDF, but CDF only does less. So if you're doing greater, that's the opposite. So you got to take the opposite of the answer. Yeah, so that making sense? So there's 3 things going on here. There's PDF, that's just for equals. And then, so there's 3 cases. Yeah, maybe I should do this. I can say this better. Here we go. So for binomial, yeah, thanks, May. You made me realize I can say this better. Binomial, case 1. If they say equals or exactly or something like that, then that's just PDF, huh? That's a binomial PDF. Case 2. If they say less than or equal to or something to that effect, then you just do binomial CDF. Case 3. If they say greater than or equal to or something to that effect, then you do binomial CDF, then 1 minus the answer.
There you go, that's easier than that.
Yeah, that's a better way to
There
say
you
it.
go, that's what I was looking for.
So there's the 3 cases.
What you're saying?
So there we go. Yeah, that is more clear. So there's 3 cases. So equals is PDF, less than is CDF, greater than is CDF with 1 minus the answer, because opposite. That's all because CDF is naturally less. Yeah, I know. It's good right there. All right, so let's keep going with our homework. Good, everybody got that down? All right. Nerdy.
Could we go over what, I know, that's the exact order we're supposed to put it in our calculator, because I've been, I have to do a trial and error,
Keep trying stuff till a reasonable answer comes out, huh?
yeah.
Yeah, on this next one we'll do it. All right, so then looking at number 9 again. Fewer than 4. So I laid out those cases for you. Fewer, but you still have to write out the reality, though, of what it means. Fewer than 4. Write out what that actually means. Guys, I can't say this enough. If somebody was to start, after all these years teaching about, somebody say, What is the thing where some people seem natural at math and some people don't? My best understanding is the people that are natural or seem to right away know what to do, it's more real for them. It's more real. It's not just numbers kind of floating on a word problem. It's real. When they look at numbers, they think 3 people, 3 pies, 3 coins in my pocket. They're real. That's what I've noticed over the years of talking to students who naturally know what to do. Math is very real to them. They're thinking real life objects. So my point in all that is try to do that for yourself more and more and more, and math will make sense. I've experienced that myself, trying to do word problems. And I still remember one time I was at Cal Poly trying to do my homework. I was at the health center, had a cold or something, waiting for my turn with the doctor, trying to solve problems. And I kept just trying to plug into this formula. It wasn't, I look in the back of the book, wrong, doing the calculation, wrong. And then I was like, all right. The doc is still not calling me in, so I'm going to go really slow now. And I'm going to read this problem and really understand what they're saying, which I didn't want to do. And I read it really slowly, tried to be real, it's 3, and I was like, oh, so then it's just boom, and it was right. I was like, yeah, you got to be real. So when you read fewer than 4, stop and get real with that. Don't try to just move some formula around. That's not how people succeed in math. It's being real. So fewer than 4, what does that mean? Just think, what if I had fewer than 4 coins in my pocket? Be real. That'd be 0, 1, 2, or 3, wouldn't it? It wouldn't include the 4. Fewer than 4 means less, not 4, right? And so then you go, okay, I got to put a 3 there. You know what I mean? And now, is that one going to be straight, or do we got to do the 1 minus? Straight, right? Because the less, remember those 3 cases I gave you, straight is just, the less is straight. Yeah. All right, let's go to number 10. Number 10. Survey showed 75%, 11 adults, no more than 1. See, they're using different words now. Be real. Don't say it out loud. Give everybody a chance. Stop for a second. Be real with that. No more than 1. Don't say it out loud. Give everybody a chance. This is the valuable stuff. So think to yourself for a second what that means. We all know the rest of the problem, right? What it's going to be. But, it's going to be a... But think, what is no more? Just real life think, what if I said, I have no more than 1 coin in my pocket? Just be real with that for a second. Don't say it out loud. Give us a chance.
Thank you.
How many does it? What are the real life possibilities?
Thank you.
If you have no more than 1. No more. Not more than 1. What's that got? Not more than 1 coin in my pocket. Not more than 1. What does that mean? Real life. What could I have in my pocket? Maybe. Or I got none. Or 1. It includes 1. If you don't have more than 1, you could have 1. Right? If I don't have more than 1, I could have 1. Or none. Right? Is that what that really means? Right? Is that what those English words mean? Not more than 1 or 0. Isn't that not more? That makes sense? Keep saying these things to yourself. They'll make more and more sense over time. This is a lot of the battle in stats, is making those words real. Not more than 1 means 0 or 1, doesn't it? Not more than 1. 1 or 0. Okay, so then, is this going to be, which of the 3 cases is this? If you say 0 or 1, is that bigger or smaller? Is that going to big, big, big numbers or small, small, small numbers? Well, it's going down to 0, so small, right? So it's going to be a less than case, right? Isn't that less than or equal to 1? Mm-hmm. So is that, so it's not, so which of the cases is it? Remember the 3 cases, less than or equal to 1. Go back here. Less than or equal, CDF straight. No need for the 1 minus.
So we'll put a 0 there then?
No, 1.
It's counting that one as well. Counting no more than 1 CDF.
So binom CDF. How many trials? There's 11. Probability is 0.75. And we'll put 1.
Mine gives me an error.
Yeah, mine does.
So that's 6. So you go,
8.10.
top 6, the opposite.
Yeah, exponent.
What's that?
There's an error in exponent 5.07.
Exponent. -6.
Okay, yeah, yeah, let me do it. I know what that means. That means move the exponent. I'll show you. So,
More stuff.
yeah, I see what you mean. Yeah, you guys getting this answer? 8.106231, blah, 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 blah. E -6, or maybe something different on other calculators. E.
So you go over 6.
Okay, hold on a second. Everybody down in with me. You're going to want to see this. This will confuse you. Is everybody down in with me? I got this. I think everybody who's doing it's getting this answer. Let me explain what this means. Does anybody already know? What does that E -6 mean?
Move back 6 places.
Means take that decimal, go back 6 places. Yeah, that means exponent. It means times 10 to the -6. It's scientific notation. Whatever. For all our needs, just move the decimal back. And since it's negative, it means back. If that was a positive 6, it would mean move forward 6 places. So take that decimal, go back 6 places. The first jump, you're at the edge. First jump, you're at the edge. And the other 5 jumps bring in zeros, right? Whoops. Does that make sense? And are we supposed to round this to what? How many places? 3. So what is it? 0.000. It's 0. There's no chance of that. That's what that means. Question. Is this making sense? Our answer was 0, wasn't it? Is that what they want on it? You guys type in, they want just straight 0? Yeah, so just 0.000, just type in 0. Yeah. Or did you actually put in 0.000? And they took it that way? Great. Is that good? So is that significantly low? Yeah. Yeah, it's really, really low. It's below 5%. In other words, if you're asking, if there's a 75% chance that adults need eye correction, you grab 11 people, the chance you're only going to have one person is super low. There's basically no chance of that. Is that good? Shall we move on? We're about done with this section. I was hoping to start the next one. Number 11. Find the indicated probability. Based on a poll, 40% of adults believe in reincarnation. Assume that 8 adults are randomly selected. Find the indicated probability. What's the probability that exactly 7? Yeah, so go through all the parts. What's the probability of exactly 7? We okay if I skip out of this at this point?
12.
We got this down. These are kind of all the same.
13. So when it says probability of all, so it'd be 8.4 and an 8 again, right?
Yeah. What's that? It's
A B. So it says the probability that all the selected adults believe in reincarnation.
Oh, yeah.
8.48.
Yep. Yeah, so this making sense? How are we doing? Seems like we're all in kind of different places. Everybody with me here on part A? Let's make sure we're all good. What do you do for exactly 7?
PDF.
Yes, remember those 3 cases? PDF. That one's a PDF, right? So I'm just going to write PDF. And it was, 8 adults. What's the probability there? 0.40. 0.40. And 7. Okay, what about part B? All of the adults. That's 8. Is that PDF, CDF? What is that? Is that exactly equal to a number, or is that greater or less? If I said all, you're asking 8 people, what's the chance that all 8? That's PDF. That's exactly, isn't it? That's PDF again. Like Val was saying, it's 8.48.
So you're just doing all of it, okay.
Yeah, because that's all, right? That's all means exactly 8, doesn't it? So that's PDF again. We good there? In part C, at least 7. At least 7. Let me pause and give you a chance. What does that mean? What does at least 7 mean? 7, 8, etc., right? We're only going up to 8 here. So 7 or 8. Right? Doesn't it least 7? At the least, at the lowest, 7. Could be more, right? At least 7 means 7 or 8, doesn't it?
So you would do them 1 minus.
So that's going to be the 1 minus, isn't it? But careful.
But you do opposite.
Yeah, because we're doing opposite, right? So it's going to be CDF, isn't it?
CDF.
Because 7, 8 is greater. Right, let's go back here and see the little thing. So for greater, we do CDF. We got to do 1 minus the answer, huh? We good? Okay. So we got to do the opposite, right? So 8.40, but here, now think with me. What number? Okay, this is what messes people up right here. 7 or 8, right? That's at least 7 or more. But we're doing I got to do 1 minus. I forgot the 1 minus there. 1 minus, or I'll just write it below. 1 minus the answer. If you want, you could just put the 1 minus right there. Either place, whatever. Anyway, what number goes in the last spot? Good, 6. Because that's the opposite of 7 or 8. It's 6 or below. Huh? Yeah. We good there? This starting to make sense? Seeing the different cases? And then you got to do 1 minus the answer. And then they just ask you if it's significant or not. That's just the 0.05 thing. All right. If you're good, I'm going to just start the next. Because we got to do 2 sections next time. So I'm just going to